Hi, I'm Maurice Dupre, and in this section we're going to discuss trigonometric substitutions. Let's begin with a quick review of the substitution process and see how we can modify it to our advantage. Normally, when we talk about substitution, we look for an integrand of the form f of g of x times g prime of x dx, and we then make a substitution. For instance, here we substitute u equal g of x, in which case du would be g prime of x dx, and so there's du, there's f of u, and so the integral becomes simplified in the sense we have the integral simply of f of u du. Suppose we turn this around. Let's look at the integral of f of u du. One thing we can do, in effect, is parameterize the u as some function of x. So if u is g of x, then du would be g prime of x dx, and we can reverse the process. In other words, if this is to our advantage to use this type of substitution, sort of a parametric substitution, and then if this integral can be done, then in the end we can substitute x equals the inverse function of u. And so consequently what we need to look for is a parameterization which can be inverted. To see how we can use this, let's begin looking at integrals with certain types of radical expressions which are very common. Square root of a square minus x square, square root of a square plus x square, and square root of x square minus a square. Now the idea here is to remember what trigonometric identities do. For instance, if x was equal to a sine theta, then this becomes a square times sine square theta, and so we can factor the a square completely out, and the radical will simply become a times the square root of 1 minus sine square theta. Notice 1 minus sine square is cosine square, so we get a times the absolute value of cosine theta. Quite a bit simpler. Down here, I can use the identity that 1 plus tangent squared is secant square. Thinking of that, let's try x equals a tan theta. In that case, here I would have a square plus a square tangent square theta. Again, factoring out the a, what we have is simply a times the absolute value of secant theta. Over here, I can use just the reverse of the previous Pythagorean identity. That is, secant square minus 1 is tangent square. And so likewise here, if I were to see this type of radical expression, I could set x equal to a secant theta, and the radical would become simply a absolute value tangent of theta. In this case, if I could simplify the integrals in terms of theta and actually accomplish the integration, in the end, what I would be looking at doing is solving for theta in terms of x. Well, notice sine of theta here is x over a, tangent of theta here is x over a, secant of theta here is x over a. And so consequently, we're dealing with theta is the sine inverse x over a, or here theta is the tan inverse of x over a, or here theta is the secant inverse x over a. So let's look at this in a little more detail. Here in this picture, I have a triangle, which it makes it easy to remember. Imagine an angle theta such that the sine of that angle is x over a. In that case, x equals a sine theta. Notice here's the triangle. Sine of the angle is opposite over the hypotenuse, so it's clearly x over a. The Pythagorean theorem tells us that in this triangle, the remaining side has to be square root a square minus x square. So consequently, here, this side divided by a is cosine theta. And so consequently, we can remember that the cosine of theta times a is the radical. Now, technically, here we'll have substituted x equal a sine theta, so we have the square root of the square. We're getting the absolute value. So remember, to go backwards in the end, we'll be looking at theta equals sine inverse x divided by a. Now, where does this make sense? Notice, if you see a radical like this, then your integrand, the function involving such a radical, can only be defined for x having absolute value less than or equal to a. We'll assume a here is a positive number. For simplicity, it's just notation. And so we're dealing with the sine inverse x over a. So remember, here's the graph of sine inverse x over a. Theta equals sine inverse x over a. And so the values of theta go from negative pi over 2 to pi over 2, as the values of x over a go from negative 1 to 1. Notice their nice invertible function. Well, we've seen how the identity cosine square plus sine square equals 1 can be used to simplify a radical of the form square root of a square minus x square. In the case where we have the square root of a square plus x square, we want to use the tangent. Let's look at a picture for that. Here, when I see the radical square root of a square plus x square, I realize that if x is a tangent of theta, if x is equal to a times tangent of theta, then this whole radical becomes a times absolute value of secant theta. After all, if x equals a tan theta, that's the same thing as saying the tangent of theta is simply x over a. If I make a triangle whose tangent is x over a, that is the tangent of the main angle here, theta in the picture is x over a. So make the vertical side have length x, the horizontal side have length a, and then by the Pythagorean theorem, the hypotenuse must have length square root of a square plus x square. Well, if I asked you what is the cosine of the angle theta, that would be a over this radical, and so consequently the secant of the angle theta is the radical divided by a, and therefore the radical itself is a times the absolute value of secant theta. Well, notice what this means. We'd be substituting tangent of theta equals x over a. Consequently, that means theta itself is the tangent inverse of the quantity x over a. And so if I had an expression like this in an integrand and I integrated it after substituting in terms of theta, my final answer would have totally a function of theta, and so consequently, in order to get back to x, I'd have to replace the theta everywhere by tangent inverse x over a, and every time I have this radical coming out, I would substitute, every time I have the secant theta, that would be the radical. Well, what about the inverse tangent? Notice that the inverse tangent is defined for all x, and so consequently, setting theta equal tan inverse x over a, the variable x can vary anywhere from negative infinity to infinity, but as it does that, the tan inverse x over a will only go from negative pi over 2 to pi over 2, and of course, it never reaches those values because they only get there asymptotically. Well, let's use trigonometric substitution to evaluate an integral. Here I have the definite integral from negative 2 to 2 of dx over 4 plus x squared. We can notice that this integrand is an even function. Replacing x by negative x gives the same value. And so consequently, the definite integral from negative 2 to 2 is simply twice the definite integral from 0 to 2. And now Notice we have down here in the denominator 4 plus x squared, and so if I make the substitution x equals 2 tan theta, then x squared is 4 tangent squared theta, and so consequently 4 plus x squared will be 4 secant square theta. Now, if that's the case, then dx itself is 2 times the derivative of tangent theta, which is secant square theta, d theta. And so now we can substitute in. We have 2. Well, what about our limits? When x is 0, that corresponds to theta being 0 for the tangent. And when x is 2, that corresponds to tangent of theta equals 1. After all, what do we have here? Theta is tan inverse x over 2. So when x is 0, tan inverse of 0, that's 0. When x is 2, tan inverse of 2 over 2, that's the tan inverse of 1. What angle has tangent equal to 1? Remember, that's the 45-degree angle, or pi over 4. And so we're going the definite integral from 0 to pi over 4 of dx, that's 2 secant square theta d theta, divided by the 4 plus x squared, that's 4 secant square theta. And so consequently, notice the secant square thetas cancel out completely. 2 divided by 4 is a half, times 2 is 1, and so we just get simply the integral from 0 to pi over 4 d theta, and of course that's simply pi over 4. Well, let's use trigonometric substitution to work out an indefinite integral. Here we have the indefinite integral of the quantity square root of 25 minus t squared, all in the radical. So what we want to do is substitute t equals 5 sine theta. That is sine theta is t over 5. dt, of course, is then 5 cosine theta d theta, and the radical itself, we see, is simply 5 cosine theta. And so this becomes indefinite integral of 5 cosine theta, there's our radical, times dt, which is 5 cosine theta d theta. 5 times 5 is 25, can come out of the integral, so we have 25 times the indefinite integral of cosine square theta d theta. Well, here we want to remember our double angle formula for cosine. That tells us cosine square theta is 1 plus cosine 2 theta divided by 2. And so our first integral of 1/2 is very easy. 1/2 d theta, the indefinite integral, is just 1/2 theta. So we have 25 times a half theta, or 25 halves theta, plus 25 halves times the indefinite integral of cosine of 2 theta d theta. Now the antiderivative of cosine is sine, and so obviously the antiderivative of cosine 2 theta is sine 2 theta over 2. So we have 25 halves theta plus 25 halves times sine of 2 theta divided by 2. 2 times 2 is 4, and so we really have 25/4 sine of 2 theta. What can we do here? Well, what we have to remember is the double angle formula for sine. Sine of 2 theta is 2 sine theta cosine theta. So consequently, when I substitute 2 sine theta cosine theta in for sine 2 theta, we'll get a cancellation of this 2, and we'll be back to 25 halves. So let's look to see how that goes now. So far we have 25 halves theta plus 25 fourths sine 2 theta. We're going to use the double angle formula that says sine of 2 theta is 2 sine theta cosine theta, and so the 2 cancels with the 4, leaving 25 halves sine theta cosine theta. On the other hand, we know the theta is sine inverse t over 5. That's because sine of theta is t over 5. The cosine of theta is the radical over 5. And if it helps you, make a little reference drawing a reference triangle. Theta is right there. We want the sine of the angle to be t over 5. Opposite over hypotenuse, t over 5. So the horizontal side is the radical, 25 minus t squared. What's the cosine of the angle? Horizontal over 5. That's radical over 5. So now notice, everywhere I see a sine theta, I replace it with t over 5. Every place I see a cosine theta, I replace it with radical over 5. And so our integral, square root 25 minus t squared dt, then becomes 25 halves sine inverse t over 5 plus 25 halves t over 5 radical 25 minus t squared all over 5. And notice the 5 times 5 is 25. They cancel. And of course, in the end, we have to remember to add the big capital C. Let's look at an integral involving a radical where we have to use secant for our trig substitution. Here I have the indefinite integral of the square root of the quantity y squared minus 49, and all that's to be divided by y, integral of that dy. So what we want to do clearly when I see that is make use of the identity secant square minus 1 is tangent square. So I'll set y equal to 7 times the secant of theta. And so that means y divided by 7 is secant of theta, or theta is secant inverse y over 7. What about the radical? Well, secant square times 7 squared is 49. We can factor out the 49 and then take it out of the radical. It becomes a 7 times radical secant square minus 1, which is radical tangent squared, which is tangent. So the radical y squared minus 49 becomes 7 tangent theta. Or in other words, the tangent of theta is the radical y squared minus 49 divided by 7. What about dy? If y is 7 secant theta, then dy is 7 times the derivative of secant theta, remember, is secant theta times tangent theta d theta. And so consequently, when I do the substitutions here, the integral becomes integral of, first the radical, well, that's the 7 tan theta, divided by the y, which is the 7 secant theta, multiplied by dy, which is 7 secant theta, tan theta, d theta. Well, notice we can cancel 7 secant theta, 7 secant theta. We can take this 7 out, and we have 7 times tangent square theta d theta. So we have finally simply 7 integral of tangent square theta d theta. So let's go to a new sheet and work that one out. We have 7 times the indefinite integral of tangent square theta d theta. Here what we want to do is remember the trig identity tangent square theta is secant square theta minus 1. So we will replace tangent square by secant square theta minus 1. Why do we do that? Because the antiderivative of secant square theta is tangent of theta. So we get simply 7 times tangent theta minus 7 times theta. Well, what was 7 tan theta? That was the whole radical we began with in the numerator, square root y squared minus 49, and minus 7 times theta. Well, remember, y is 7 secant theta, so y over 7 is secant theta, and so theta itself is secant inverse of y over 7. And so here we have secant inverse of y over 7. And then don't forget to add the big capital C. So the end result is the indefinite integral square root y squared minus 49 all over y dy equals square root of y squared minus 49 minus 7 times secant inverse y over 7 plus c. Let's use trigonometric substitution to work an indefinite integral. Here I have the indefinite integral of dx over the quantity x squared times radical inside x squared minus 1. And so consequently, the thing we realize is we want to make use of secant square minus 1 as tangent square. So I'll set x equal to secant theta. Then dx is secant theta tangent theta d theta, and square root x squared minus 1 is equal to tangent theta. Well, let's see, we want to get everything in terms of theta. What about this x squared? Notice x squared minus 1 is tangent square theta, or x squared is secant square theta. So consequently, when we substitute in, we get the indefinite integral of dx is secant theta, tangent theta, d theta, all divided by the x squared is secant square theta, and the radical is tangent theta. So notice the tangent thetas cancel, and secant theta cancels with one of the secant squared. We end up with simply the integral d theta divided by secant theta. Well, how do I possibly anti-differentiate 1 over secant of theta? Well, let's remember, secant of theta is the reciprocal of cosine theta. So 1 over secant theta is cosine theta. This is the cosine theta d theta, indefinite integral of cosine theta d theta, and of course the antiderivative of cosine is simply sine. So we have the sine of theta. Well, how can we figure out what the sine of theta is? Let's draw our reference triangle. X is the secant of theta, and that means the cosine of theta is 1 over x. So let's draw our reference triangle. Draw a little angle theta. And I want the cosine of theta to be 1 over x. Well, cosine theta adjacent over hypotenuse, make the hypotenuse x, the adjacent side 1, and now the opposite side is what? Square root of x squared minus 1. Notice the tangent of the angle theta is the radical divided by 1. That is exactly what tangent theta is, the radical. On the other hand, what's the sine of theta? That's opposite over the hypotenuse. So sine of theta is square root x squared minus 1 divided by x. So there's our antiderivative, and don't forget to add the big capital C. Let's use trigonometric substitution to work an indefinite integral. Here I have the indefinite integral of 8 divided by the quantity w squared times the radical 4 minus w squared, all dw. So we want to find the antiderivative of that expression, and I see that radical right away. I want to substitute w equals 2 sine theta. So then dw is 2 cosine theta d theta. Notice, since w is 2 sine theta, w square is 4 sine square theta. So now we can easily substitute for everything we see in this integral. We have 8 times the indefinite integral dw is 2 cosine theta d theta. Down in the denominator, w squared is 4 sine square theta. And then the radical, well, what's the radical? If w is 2 sine theta, then w squared is 4 sine square theta, and so the whole radical is simply 2 cosine theta. And so consequently down here we have 4 sine square theta times 2 cosine theta. 4 times 2 is 8, and so those cancel out. And so now our integral becomes 2. Well, let's cancel cosine thetas. And so we have 2 integral d theta divided by sine square theta. Well, remember, 1 over sine is cosecant. So this becomes twice the integral of cosecant square theta d theta. Now remember, the derivative of cotangent is negative cosecant squared, so the indefinite integral of cosecant square theta is simply negative cotangent theta. So we have negative 2 cotangent theta. Well, we need to get back to sines and cosines because the sine of theta is w over 2, and the radical over 2 is cosine of theta. And so we look at this expression cotangent of theta, and remember cotangent is cosine over sine. So we have negative 2 cosine theta divided by sine of theta. And so now we can go back. The radical divided by 2 is cosine theta, so we have radical 4 minus w squared all over 2, and the sine of theta is w over 2. And so notice those 2's cancel, and we simply get finally negative 2 radical 4 minus w squared over w, and then don't forget, add the big capital C. Let's work an indefinite integral with the trigonometric substitution method. Here I have the indefinite integral of v squared divided by the quantity 1 minus v squared raised to the 5/2 power. So in effect, the 5/2 power is the radical 1 minus v squared raised to the 5th power, and so I see to simplify that, what I want to do is set v equal to sine of theta. Then 1 minus v squared is cosine square theta, and so 1 minus v squared to the 5/2 is cosine to the 5th theta. On the other hand, dv is cosine theta d theta. So let's substitute in. In the numerator we have v squared. Well, v is sine theta, so our numerator becomes sine square theta from the original integrand, but then we have dv, which is cosine theta d theta, and all that's divided by the radical, which is now cosine 5th theta. We can cancel one factor of cosine in the numerator with the denominator, and so we'll have sine square over cosine to the 4th. So let's write that as integral sine square theta divided by cosine to the fourth theta d theta. Now, as it stands, what we can do to simplify this is view that in the first place as sine square theta divided by cosine square theta times 1 over cosine square. We have another factor of cosine square down here, but 1 over cosine square is secant square theta. And now sine over cosine is tangent. So we have the integral of tangent square theta times secant square theta d theta. And now here we realize we have an easy substitution because the derivative of tangent is secant squared. So if I substitute w equals tangent theta, then dw is the secant square theta d theta. And so this simply becomes the integral of, let's come over here very simply, integral w squared dw. So let's carry that integration out. We have w equals tangent theta, and we're integrating w squared dw. Well, that's simply w cubed over 3. So we have tangent cubed theta over 3. Well, now to go back, let's rewrite the tangent as sine over cosine. So we have sine cubed theta over cosine cubed theta. And so remember, the cosine is the square root of 1 minus v squared. Let's just write this over here. The sine of theta was the v, and the cosine of theta is the square root of 1 minus v squared. So we have 1/3 v cubed divided by square root of 1 minus v squared cubed. And then don't forget to add on the big capital C. Well, we've worked some indefinite integrals and definite integrals using trigonometric substitution. Now that you've seen these worked, you should try some on your own.